Hello everyone, I'm Chang Zhongli. In this video, I will present our work titled An Embarrassingly Simple Backdoor Attack on Self-Supervised Learning. Let's first establish a brief understanding of self-supervised learning. At its essence, self-supervised learning is a learning paradigm that harnesses the power of unlabeled data to learn high-quality representations. A pivotal method within self-supervised learning, which our paper focuses on heavily, is contrastive learning. This approach is about learning representations by contrasting positive pairs against negative pairs. The strength of self-supervised learning comes from its learned, high-quality representations and good performance across many machine learning tasks, making it a representative approach in the field. Self-supervised learning is cost-friendly without labeled data and offers stronger robustness against adversarial attacks than supervised methods. Backdoor attacks are a growing concern in machine learning. Simply put, during a model's training, specific patterns or triggers are secretly added. After this, during the inference phase, the model seems to work as usual. But when it comes across these hidden triggers, it behaves differently, just as the attacker planned. Most of the research on this has looked at supervised learning, where triggers are tied to a target class using labels. But in self-supervised learning, we don't have these labels, so the old methods don't work. Our research aims to solve this challenge. As we explore the potential vulnerabilities of self-supervised learning, several pivotal research questions emerge, guiding the trajectory of our investigation. Firstly, we raise the question, is self-supervised learning as vulnerable to backdoor attacks as its counterpart, supervised learning? This question seeks to establish a comparative framework, discerning the relative robustness or vulnerability of these two prevalent learning paradigms. Subsequently, we delve into the underlying mechanism that might render self-supervised learning vulnerable. It's imperative to understand the mechanisms within self-supervised learning that adversaries could potentially exploit. To answer these questions, in this work, we propose CDRL, standing for Contrastive Trojan Learning. This innovative method is a self-supervised backdoor attack. At its core, CTRL embeds stealthy, augmentation-resistant triggers, like spectral triggers, within the learning process. These triggers, operating subtly in the frequency domain, remain robust against common data augmentations and are visually undetectable. The essence of CDRL lies in its exploitation of data augmentation and contrastive loss. By manipulating these foundational components of self-supervised learning, CDRL introduces backdoors that profoundly impact model behavior. We now turn to this table to highlight CDRL's effectiveness. Clearly, CDRL achieves the highest attack success rates across the three evaluated datasets. When compared with earlier studies, CDRL greatly improves the attack success rate, narrowing the gap with supervised learning. This addresses our initial research question. Self-supervised learning exhibits vulnerabilities to backdoor attacks akin to those in supervised learning. To explore the mechanics of backdoor attacks in self-supervised learning, we examined class distributions within the feature space as depicted in the figure. In supervised learning, the target and trigger classes may remain separate from each other. However, in self-supervised learning, these classes are intrinsically entangled. This intertwining ensures that during inference, inputs with the predefined trigger are invariably classified into the adversary's designated target class. In conclusion, our research comprehensively examined the vulnerability of self-supervised learning to backdoor attacks. We introduced and assessed CDRL, a straightforward yet potent self-supervised backdoor attack methodology. Notably, our findings spotlight the representation invariance property inherent to self-supervised learning. While this property typically benefits adversarial robustness, it also presents unique challenges, underscoring the nuanced landscape of self-supervised learning vulnerabilities. For more details, please refer to our full paper.